In the last video, we argued that when we have two systems which are connected thermally, and one of which is a thermal reservoir, we have kind of fundamentally different statistical mechanics for the working system than we do when the working system is isolated. In particular, the states of the working system are now distributed according to the canonical ensemble rather than according to the microcanonical ensemble. One really interesting consequence of this is that prior to this, in both classical thermodynamics and in the microcanonical ensemble, we were principally interested in systems which are very large. And that's technically still true here. The combined system of the reservoir and our working system should still be large. However, we're now able to look at working systems which are themselves very small. And in particular, we can look at working systems which are just a single particle. So that's what I'm going to do today. In the next video, we'll look at the consequences of having many particles present in our system. But today we want to look just at the probability implications of the canonical ensemble on these single particle systems. So I've picked two representative examples. The first is the qubit system. This is important in quantum information and in a variety of other settings as well. And it's the quantum system that just has two states. The second system I want to look at is the harmonic oscillator, which we've looked at a bunch already in statistical mechanics. All right, so without further ado, let's hop into it. We know that our principal objective in the canonical ensemble is to find the partition function. If we can do that, we can get all the other quantities of interest that we want from the partition function. So let's find the partition function for each of these systems, and then later on in the video, we'll look at the quantities that we can get from those partition functions. All right, so for the qubit system, the states are, let's just say 0 or 1. Excellent. And the energies are E0 and E1. But because we can shift all of the energies in our problem up or down, let's, without loss of generality, say that the energy of state 0 is less than the energy of state 1. And let's, in particular, say that the energy of state 0 is just 0. So we're going to say that this is just equal to 0. Wonderful. Now let's look at the partition function. I'll call it z sub q for qubit. We know that this is in general the sum over states of e to the minus beta times u of that state. In this case, we only have two states, so we only have two terms in this sum. In particular, we have 1 plus 1 because that's e to the minus beta times 0. So 1 plus e to the minus beta e1. Great. Now, I did say that we're going to look at derived quantities later, but I want to just point out one thing from this, which is that we can now look at the probability of ending up in each of these states. So the probability of 0 is now going to be the Boltzmann factor for 0, but that's just 1, divided by the partition function. So 1 plus e to the minus beta e1. Meanwhile, the probability for 1 is equal to e to the minus beta e1 over 1 plus e to the minus beta e1. Great. And we see that as e1 gets bigger and bigger, the probability that we stay in the 0 state, in the ground state, as we would say in quantum mechanics, gets bigger and bigger. Whereas the probability of being in the excited state, E1, gets smaller and smaller. Excellent. Now let's look at a slightly different system, the harmonic oscillator system. So remember now that the states here are non-negative integers, or I should say are indexed by non-negative integers n. So n, which is equal to 0, 1, 2, ... Great. And the energies, well, we have En is equal to h bar omega times n plus 1/2. So h bar and omega are just, well, h bar is obviously a constant, and omega is just a constant specific to the system. Great. Now we want to find ZHO for harmonic oscillator, and that's going to be the sum. Now this sum is going to be over n of e to the minus beta h bar omega n plus 1/2. Now right away we see that this sum and is actually a product of two things, e to the minus beta h bar omega n and e to the minus beta h bar omega over 2. And that e to the minus beta h bar omega over 2 doesn't depend on n at all, so it can come right out of the sum. So we get e to the minus beta h bar omega over 2 times the sum over n of e to the minus beta h bar omega n. Wonderful. Let's be clear that n here goes from 0 to infinity in both of these cases. And now we want to utilize one of, I think, the most important formulas for physicists to know, the geometric series formula. Remember that the geometric series formula says that the sum, so let me say, recall, the sum from n equals 0 to infinity of x to the n is equal to 1 over 1 minus x for the absolute value of x less than 1. Great. Do we have that here? In fact, we do. Let's think about this argument of e. This argument is always positive. That means that we're always taking e to some negative number. Great. E to the 0 would be exactly 1, and e to any negative number is going to be less than 1. So we're good here. And we don't have to worry about the absolute value because e to any power is going to be a positive number. Excellent. So in our case, we can just use this without any fear, and we have that ZHO is equal to e to the minus beta h bar omega over 2 times 1 over 1 minus e to the minus beta h bar omega. Excellent. And we could leave it there, but actually there's a little bit more that we can do. We can pull out, or maybe I can say, we can multiply the numerator and the denominator by e to the beta h bar omega over 2. So this is just a fancy multiplication by 1. We see here that this factor cancels this factor. Good. In the denominator, we get e to the beta h bar omega over 2 minus e to the minus beta h bar omega over 2. So let me write that in another suggestive way by also multiplying and dividing by 2. So this is 1/2 times 2 over e to the beta h bar omega over 2 minus e to the minus beta h bar omega over 2. Excellent. And the reason I've written things in this strange way is because this quantity is the hyperbolic cosecant of beta h bar omega over 2. So this whole thing is 1/2 times CSCH beta h bar omega over 2. Great. Okay, so let's record both of these values here. I'll clean up the board and then we'll come back to it. Okay, now equipped with our partition functions, it's time to look at some derived quantities. So let's check off everything that we've finished. And the two derived quantities that we've focused on so far are the expected value of the energy and the Helmholtz free energy. Recall that we derived in the last video that the expected value of the energy is minus the partial derivative with respect to beta of the log of the partition function, and the Helmholtz free energy is minus 1 over beta times the log of the partition function. All right, so let's figure these out in the two cases that we're interested in. First, for the qubit system. Okay, so, well, first of all, let's just figure out what the log of the partition function is. That's going to be the log of this whole quantity. So, yeah, let's just say u is equal to minus partial beta log of 1 plus e to the minus beta e1. Now, recall that really what happens when we take the partial derivative with respect to beta of a log is that we get the derivative with respect to log of the argument, sorry, the derivative with respect to beta of the argument of the log over the argument of the log. So this is going to be minus partial with respect to beta of 1 plus e to the minus beta e1 over 1 plus e to the minus beta e1. Great. Okay, so if I take this beta derivative and then take a negative, what I'm going to pull down for the first, so I should say for the first term, this 1, I'm just going to get 0. And then here I'll pull down an e1. Great. So this is going to equal e1 e to the minus beta e1 over 1 plus e to the minus beta e1. You can also check using the probabilities that we wrote on the last board that this is exactly what you would get if you just attached 0 to the probability of 0 and then added e1 times the probability of 1. Wonderful. Okay, let's do the same thing for the harmonic oscillator. So that's in the cubic case. Here's the harmonic oscillator case. Here, we are going to get, well, it's a very kind of similar thing. The 1/2 will cancel in the numerator and denominator. So we'll just get d beta of cosecant, hyperbolic cosecant, sorry, beta h bar omega over 2 over cosecant, hyperbolic cosecant beta h bar omega over 2. So we need to know what the derivative of the hyperbolic cosecant is. This is not one of the identities I would have remembered, but the answer is that the partial derivative with respect to x of hyperbolic cosecant of x is equal to hyperbolic cotangent of x times hyperbolic cosecant of x. Great. Okay, so by the chain rule, we're going to pull down an h bar omega over 2. Then we're going to get our hyperbolic cosecant of beta h bar omega over 2 times hyperbolic cotangent of beta h bar omega over 2, and then divided by the hyperbolic cosecant. But this actually turns out pretty nicely. The hyperbolic cosecants cancel. And so we get that the expected value of the energy here is equal to h bar omega over 2 times the hyperbolic cotangent of beta h bar omega over 2. Excellent. So one thing that we should note is that as beta increases, this function also increases. So one of the things that we learn in actually both of these cases is that as the temperature increases, the chance of the system being in higher states also increases, which tends to increase the expected value of the energy. Good. Okay, let's figure out the Helmholtz free energies in the two cases. So these are a little bit easier to determine. For the cubic case, it's just, oops, minus minus 1 over beta log of 1 plus e to the minus beta e1. Okay, and for the harmonic oscillator case, we get minus 1 over beta log of 1/2 hyperbolic cosecant of beta h bar omega over 2. Wonderful. Now, there's something very interesting about these that I wanted to point out, which is that typically we expect the Helmholtz free energy to be extensive. But in this case, it can't be. We don't have any extensive variables that this quantity depends on, right? There's no n here because n is equal to 1. And so we get a Helmholtz free energy that is very clearly intensive, right? 1 plus something intensive, since this is the energy of a single state. And down here, the same kind of thing, a log of an intensive quantity. So that's very interesting. For one particle states, we don't have the same sort of extensivity relationships that we anticipate having from thermodynamics. That'll return when we go back to looking at systems with many particles. But the whole point of this video is that the canonical ensemble gives us a well-defined way to think about the probability distributions of states for single particle systems, and that using things like summation rules, we can often figure out exactly what the values of certain expected values and moments are in this case. That's all for this video. In the next video, we're going to look at multi-particle systems once again. I'll see you then.